So then we will continue with the next presentation. This post-processing step has been referred already several times in these previous presentation, and that just kind of highlights the importance of that stage. So the next presentation will focus on that post-processing of AM components for critical application, and that presentation is given by Hans Södervall, who is a business development manager from the Quintus Technologies. So please continue.
Okay, thank you very much for giving Quintus this opportunity to present the HIP technology. I hope everybody can see and hear me.
Yes, it is working well.
Perfect. I hope to prove that HIP is not only a challenge, but perhaps a possibility and in some cases a necessity. So let's start. This is the outline of the presentation. I will just briefly start with a short history of the HIP technology, cover a little bit about hot isostatic pressing, the effects of HIP, a little bit about the Quintus HIP presses, and also talk a little bit about the new feature with the Quintus HIP presses, which is high pressure heat treatment. Discuss also obviously HIP in additive manufacturing. So basically the HIP technology started in the mid-50s in the US. It was basically for cladding of nuclear fuel elements. Initially they were quite moderate temperatures and pressures. The work with Quintus, which actually is an ABB or ASEA company, started in the mid-50s, where they developed a new type of pressure chamber, which is a wire-wound vessel, which will allow for quite decreased footprint and also a very high safety margin. The application at that time was for the production of industrial diamonds. Currently, Quintus is focused on two business areas. It's sheet metal forming and it is material densification, both hot isostatic pressing and cold isostatic pressing. I think most, if not all of you, are familiar with the principle behind hot isostatic pressing. It's basically a uniform pressure that will apply equal pressure in all directions on a product and compact it uniformly. Today, hot isostatic presses exist for temperatures up to and even beyond 2000 degrees C. Typical pressures are in the range of 100 to 200 megapascal. Gas is in most cases argon, but other types of gases can be used too. And the actual densification process is a result of plastic deformation, creep, and diffusion. So with the possibility to use different temperatures and pressures, this is something that you can elaborate with. The design of the Quintus press, which was developed in the mid-50s, is basically that of a core of a furnace and an insulation mantle surrounded by a wire-wound yoke. And with the wire winding, we actually pre-stress the pressure chamber so that it reaches an equilibrium at temperature and pressure. And the advantage with this is that you can, of course, allow for a much reduced footprint. You don't need a very high wall thickness on the actual pressure vessel. But we also have a system which is designed to leak before it explodes. So basically a Quintus wire wound pressure vessel cannot explode. It's designed to leak. And also with our patented solutions, we can control the cooling speed. We can reach very high cooling speed with our different systems, thanks to fans and forced convection cooling. Typically today, two areas for the use of HIP, obviously densification of products, added manufactured products, of course, castings, MIM products, claddings, and diffusion bonding. I would say that the biggest usage of HIP today is probably the consolidation of casted products. Also, a fairly large area is the compaction of powder, which is basically starting from a powder as raw material, which is then filled into a pre-designed can. The can is evacuated and sealed, and it's hipped. You can have the typical, any type of geometry, I mean, from the powder-based billets, which basically are rectangular or cylindrical, to the near-net shape products, which in shape and design very much resemble the end product. A fairly large segment within the near-net shape technology today is nuclear applications. And I would say that for the nuclear segment using near-net shape, powder-based near-net shape products today, I think the main features are product reliability, product integrity, and improved mechanical properties. And I think also these arguments apply for AM-produced products. Well, what does it achieve? Well, it achieves a 100% dense material by closing all the pores. It improves mechanical properties, mainly fatigue and ductility. It also reduces the scatter in the material properties, which makes component life more predictive. And eventually, it also reduces the scrap rate. And on the right-hand side, you can see this is actually a test that we did to show the effect of HIP. So we made a mechanically induced pore in a material, and you can see that that pore, which is probably about 1 centimeter in diameter, was completely closed after HIP. You can actually see the waste, which resembles the shrinkage of the part. That's a fairly high pore, so it's quite impressive forces in place. Typically, as printed materials, we could have a number of defects. There could be basically what we are looking at is porosity, oxides, and microcracks. And obviously, these defects will have a negative influence on mechanical properties like fatigue, ductility, and also fracture toughness. And with using hot isostatic pressing, you are able to remove these pores, which will then have an effect on the mechanical properties, as I mentioned. And I would say the fatigue life is probably the dominant property that will be affected. We've seen that it can be extended by 10 to 100 times. And also one important thing is to mention is that lowering the scatter of the properties. You do get an improved surface quality and also increased form stability, which will lead to a lower rejection rate. This is an example of a EBM 316L part that just shows that the pores on the micrograph are evident in an as-built situation, but after hip pores are reduced. Also, what we can see is that positioning on the build plate has an importance or has an effect on the porosity. And this is something that we've seen in tests together with customers. And one way of reducing the scatter or variation in porosity is to perform a hip afterwards, where you can completely remove all the variations in porosity. You mentioned scatter, reduction of scatter. I think this shows that even though we do not see in this particular case an improvement in the maximum tensile and yield strength, we can definitely reduce the scatter of the test results with a 3 to 4-fold. This is for a nickel-based superalloy. Also looked at ductility and reduction area. We not only do we see actually an improvement in the mechanical properties, but again, there's a reduction of scatter. Typically, this is for titanium 6 for aluminum alloy, titanium 6 aluminum alloy, sorry. And we can see that the mass cast fatigue results are quite poor compared to the results from after hip and the Densol process. I mentioned before high pressure heat treatment. Typically a thermal process for not only AM parts but for many parts could typically look like this, where you would basically have a number of independent thermal processes, and you would have stress relieving before moving the parts on the build plate, and then you would have a hip cycle performed, and then you would remove it from your hip press, and then you would have a solution heat treatment. And finally, as a fourth step, you would have the aging process. With the Quintus high pressure heat treatment possibilities, you can actually perform all these steps in one single machine. I would rather look at our presses as heat treatment furnaces with high pressure capabilities. I mean, the obvious advantage is, of course, that you can reduce your lead times quite a lot, which will, at the end of the day, save money. And it also gives you an excellent process control. And I think these are key important factors when looking at the hip and remembering that it's not only a challenge or an added cost, but it can actually give the customers possibilities to reduce lead times. Quintus presses come in a number of variations. One, I would say, more standard type is our uniform rapid cooling. A little bit depending on size of the hip, we can reach between 150 and 500 C per minute cooling rate. And this is 100% controllable, so you can basically set the cooling rate that you want. And it will definitely shorten your cycle times in the hip and increase your productivity. If you have products that need quenching or considerably higher cooling rates, we have the uniform rapid quenching, which can reach up to 3,500 C per minute gas temperature. the difference between the URC and the URQ is very much similar to quenching. It's once the quench cycle has started, it will quench down to the set temperature. If you need a controlled cooling, the URC would be the choice. What we've seen is that we will have an even temperature distribution, and the temperature accuracy, both in heating up and cooling down, are excellent. And we are able to reduce the thermal stresses, which could lead to cracking. And we talked a little bit about distortions also, and with the Quintus press, that we see no distortions or complex products or products with different material thicknesses. And also, so one thing that we do is that we can keep the pressure at a certain limit during quenching, which will push the transformation curves to the right, so that you can avoid any type of phase transformation that we need to. If you look about the typical AM process flow, compare it with what can be achieved with Quintus high pressure heat treatment, typically you would print to perhaps 99.99%, and then you would have the HIP, and then you would have your subsequent heat treatments done in separate thermal processing units. With the Quintus high pressure heat treatment, you can actually keep the product in the HIP and do your heat treatment and aging in the same HIP cycle. You can also elaborate a little bit with printing speeds, so you don't necessarily have to print to a very high density. You can perhaps print a little bit faster, which will result in a lower density before HIP, but after HIP you will have 100% density. There has actually been some work done on that. This is for titanium. It's in Germany. It is some PhD work thesis that is just recently published, where they have increased the printing speed with 67%, which has reduced the build time with 26%, which in turn led to an overall cost savings of 50%. And by elaborating with different types of HIP cycles together with that, we can actually achieve mechanical properties that are well within limits. So the standard HIP cycle for titanium is 920 at 100 megapascal, 2 hours furnace cool. But we've proven that you can both go down in temperature and up in pressure and achieve mechanical properties that are sufficient. So there's possibilities to elaborate. However, I mean, standard dictates that it should be 920, 100 megapascal. There are possibilities to increase speed and increase productivity. So basically, to finish off, the HIP technology will provide improved mechanical properties, and also not only that, but you can control the process, and you can also achieve productivity gains using the press as a heat treatment furnace, which will give you shorter lead times and improve material properties. Fatigue, as I mentioned, is greatly improved with the HIP process, and also the yield strength by having the possibility to optimize or vary the HIP parameters, which are the pressure, time, and temperature. You can improve your mechanical properties. And obviously today, I mean, many of the standard specifications are for conventional manufacturing processes. I think we mentioned a little bit about standards and the work that needs to be done there. And also, I think it's important that we do not need to print to very high densities. I mean, we can print go for a lower density and still reach 100% densification. So I think with that, I would like to say thank you.
Thank you so much, Hans. He will be also available for the separate question and answer session in the Teams, so that there will be actually then 2 parallel sessions. So Hans and Steve will be both on their own sessions. There is a question from the audience, because you mentioned that the hipping is used quite a much in the nuclear sector. So can you disclose information on some components produced by HIP for nuclear applications?
I could mention in general terms, yes, I would say it's typical large bore bends, T-pieces, there are valve bodies, pump bodies. That would be typical applications. Fairly high wall thickness, we're talking 1 to 2 inches.
Okay, thank you. I have another question. So I think that in general, when we talk about the post-processing, there is a lot of room for the automation to increase the productivity of this whole AM production. So I was wondering that at the Quintus, have you had any activities in this field to kind of to go towards higher automation?
Definitely. I mean, we try to stay ahead of the game, and that's probably a big challenge for us. But for sure, there are discussions ongoing. How can we take a traditional batch process, for instance, and make it more streamlined for inline production? But I would say that is a project and a process that's just started, but it's for sure something that we have on our wish list going forward.